to talk about a new model for quantum mechanics that emphasizes on the interaction between classical information and quantum information. Most of the results are based on my master's thesis, which is a continuation of the work of Jamie Bicker. More precisely, we will look at how to combine the category CP star of data Frobenius algebras and two categorical models for quantum mechanics. Alright, so first I will just revise the two models that we know already. So CP star, special data Frobenius algebras, and two categorical quantum mechanics. Then I will talk about the theory of bimodules because this is useful to make a more general, more rigorous two categorical construction. And then we will look at how we can combine these two constructions. This model gives us a nice way to describe quantum teleportation and classical information, and a nice way to give a unified security proof. Alright, so first of all, CP star is a construction on the modal categories, which gives us a new modal category where the objects are special data Frobenius algebras. So here are the graphical representation. These are algebras which are associative, which have a unit law, Frobenius laws, and this is the specialization. And the morphisms between the Frobenius algebras are completely implicit morphisms, which are basically morphisms F, such that there is a G for which this equation holds. This is a very nice way to describe classical and quantum information because commutative special data Frobenius algebras exactly describe the copy and deletion property of classical information. And when we look at non-commutative data Frobenius algebras, these are products of matrix algebras. So these represent quantum information. Alright, the other model, the two categorical model. Two categories, for those who are not very familiar with it. Actually you are, because monoidal categories are special cases of categories. Two categories consist of objects, morphisms, and morphisms between the morphisms. So we will call these one cells, and these regions represent the one cells, and they will zero cells. Sorry. Yes, and these are interpreted as the classical information. Then we have one cells. So in monoidal categories, they are normally represented like this. These represent the quantum systems. And in the two categorical language, they are lines between two surfaces. Then we have two cells, so morphisms between the morphisms. Normally they are represented like this. And in the new diagrams, they are the vertices between the one cells. And these represent quantum domains, so morphisms between the quantum systems. We can compose one cells and two cells horizontally. So, like this. And in the two categorical diagrams, this is just a matter of like composing, just pasting the two diagrams together. And then we have vertical composition, which would be something like this. And in our diagrams, that would be like this. Alright, so the standard example for two categorical quantum mechanics is 2-hill. Here the zero cells are given by natural numbers because these represent the equivalence classes of classical structures. So here the regions are marked with C, so this is like the one-dimensional Hilbert space, C2, the two-dimensional Hilbert space. This is just an example to illustrate it. The one cells are given by matrices of finite-dimensional Hilbert spaces. So here, this one is a one cell between a one-dimensional classical structure and a two-dimensional structure. So this will be a 1 by 2 matrix, so a vector whose coefficients are Hilbert spaces. And this one is a 2 by 1 matrix. And two cells are given by matrices of linear maps, where the entries of this matrix are the maps that lie between the corresponding entries of the one cells. So horizontal composition here is given by matrix multiplication, or at least a generalized way of that. So we take the tensor product of H1 and H3, and tensor product of H2 and H4, and then we take the byproduct of the two Hilbert spaces. And so this also works for matrices and for vectors. Let me go back. So it's not really clear how to combine, on the one hand, 2 Hilb with the abstract C star construction. What we like to have is a more general description of the 2 category, which corresponds to these diagrams. So a good way to start off is to see if we can give some sort of interpretation to these diagrams. So one way to do this is, by the way, time flows up here. So yeah, the one cells will be our physical object, and the 2 cells will be the morphisms between them. And we can see this as, we can look at it from the decoherence perspective of quantum mechanics, which means that a quantum system that interacts with its environment will start behaving like a classical system. And in that way, we can characterize quantum systems as the one cells between trivial zero cells, because this will be a matrix with only one entry, so a Hilbert space. And we can characterize classical information as matrices of one-dimensional Hilbert spaces, which is just a decomposition of a Hilbert space. Alright, so this interaction with the environment, we can describe this mathematically in terms of modules. The environment will be represented by the classical structures A and B. The physical object will be M, and there's a map between M and A and B, which represents the flow of information about M to its environment. This has to satisfy some rules. So, for instance, if we have a flow of information and then we copy the information, it's the same as when M interacts with its environment and then it interacts again with its environment. Also, if information about M flows to its environment but then we delete the information, then this is the same as when nothing happens. So it stays a quantum system. And also, we want this flow of information to be well behaved under time reversal. Morphisms between modules should be protected from decoherence. So if we first apply morphism and then it interacts with its environment, it should be the same as when there's first an interaction and then a morphism. And this is very important if you have quantum protocols, because we cannot always control when this interaction takes place. So if we don't have this, we don't know if quantum protocols will be well defined. Alright, so it will be more convenient to take the dagger of all these features, which we can do because of the last. So how can we use this to give a general 2 construction, which turns a modal category into a 2 category? So if we look at the example of Hilbert spaces, we see that one cells were the natural numbers, and these represent classical structures, so we will do the same in this construction. Sorry, zero cells, yeah. One cells are matrices of Hilbert spaces, which are bimodules of classical structures in Hilbert, so in our general construction we will take the same again. And 2 cells linear maps. So we recently found out that in representation theory this type of construction is also used, and it's called the orbital condition model category. So some properties of this construction are that if you apply to a monoidal category, this is actually a 2 category, so it's a great, that's what we need. We have good reasons to believe that it's a symmetric monoidal 2 category, but that's a very proof with a lot of things to check. So, also, this construction preserved the dagger, which means that we can fit the diagrams. If C is compact, then so is 2 of C, so in the sense that every one cell has ambidextrous duals. If C has dagger byproducts, so they're all home categories of 2 of C. And the subcategory of scalars of 2 of C corresponds to C. And 2 of F help is isomorphic to the category 2 help, so this is a good generalization. So all these proofs can be found in my master's thesis. So I haven't told you much about this category yet, only its elements, but we need to talk about composition as well and coherence laws between the compositions. But I will restrict myself to horizontal composition of 1 cells. The rest will be a bit similar. This is given by the following co-equalizer. So I need to explain the notation a little bit, and I'll just go through the concept of co-equalizer quickly. So this is given by a map pi, such that this diagram commutes, where NB is the right action of M, and Bn is the left action of N, B. So we need such a map that makes this compute, and that whenever we have another map F, such that this commutes as well, then this factorizes through pi. So this is a very theoretical description, and it basically captures the idea that the horizontal composition of M and N should be the subspace of the tensor product of M and N, the biggest subspace of this tensor product, such that if we take values from M and from N, they should correspond to at least one value in B. But so we don't know what it looks like yet. We just give this general description. So can we find this module explicitly? Yes, we can. So if we have a morphism F like this, then it turns out that it factorizes through M dot N, and this is just short for this module over here. I will quickly go through the proof. So here we have F. This is the identity, because of the identity law for bimodules. Here we use the composition law for bimodules. So one interaction with the environment, and then another one is the same as copying. And then, because of our assumption, we can move this M over here to the other side, and it becomes this N over here. So F factorizes through M dot N. However, this factorization is not unique, so it doesn't give us the co-equalizer immediately. But we've proven that finding the dagger co-equalizer is the same as finding a dagger splitting of this, which is, by the way, an idempotent, which follows from the dagger rule for modules. Alright, so now we have a general description of the 2 categories that we want to work with. And as I said before, we want to express quantum teleportation protocols and the security of that in this category. But for that, to prove the security of that, we need to have a deletion map for every object, because security basically means that if we delete the outcome of the teleportation, then all information is lost. But that doesn't exist in every category, for example, not in F hill. So that's why we want to combine it with CP star. So now we're going to look at the category 2 of CP star of F hill, or 2 of CP star of any monoidal category. And it would be interesting to find out if we can make a generalization of CP star, which works on two categories as well, and not just on neither categories, and then see if this such a diagram would commute. But this is not that obvious at all, because first of all, for this 2 construction on CP of F hill, we need a classification of all classical structures in CP star hill, which doesn't exist. So we did make some progress on this. We proved that there is a correspondence between special Frobenius algebras and classical structures in C and finite groupoids. So I understand that this will be a bit confusing. So we're looking at classical structures in CP star of F hill, and the elements of CP star of F hill are data Frobenius algebras. So what we've proven is something about classical structures on classical structures of this, and actually we've done a little bit more general, because we have a correspondence between special data Frobenius algebras and classical structures.
You mean F hill there, not C? That on the very last one.
Ah, yes. Oh, I'm sorry. Yeah, this should be F hill. All right. But there's another problem as well. That is that CP star of F hill does not have all product classes. We also give a counterexample for this, which makes it hard to show that this construction is well defined for the entire category. So there's lots of things that we're going to work on. But we do know enough, because we do know that there is a subcategory in 2 of CP star of F hill, which is good enough for our purposes. And this is analogous to category 2 hill. The 0 cells are natural numbers, 2 cells are matrices of data Frobenius algebras, and did I say it right? So 1 cells are matrices of data Frobenius algebras, and 2 cells are matrices of completely positive maps. So we're almost there. We can almost give you the representation, the teleportation protocol. But we need to have some notion of measurements. So we will define it like this. Measurements are co-unit preserving 2 cells of this type. So the white areas are the one-dimensional Hilbert space, so the unit object of the model 2 category, and the colored areas, they can be any zero cell. So the input is a quantum system, and the output is a classical system. And this definition, we applied on algebras Cn, are exactly stochastic maps. And if we apply it on B of H, they are exactly theorems. So here's the proof. The co-unit preserving condition is given like this, which corresponds to when we take the dagger. And now we have a completely positive map from a classical structure to quantum space, quantum structure, which is defined on the basis elements of Cn. So this gives us the sum of positive elements on the one side and the unit elements in our space on the other side. So on Cn, this corresponds to a stochastic map, because this is exactly a map that preserves probability distributions. And on B of Cn, this corresponds to a theorem. Alright, so we're running without sleep. This will be easy to follow without the whole theory behind it, because now we're going to talk about the teleportation and classical encryption in our diagrammatic language. So we can give a unified description of quantum teleportation and classical encryption. And it's given by this diagram, where mu is a measurement, as we defined before, and mu is a unitary 2-cell. Alright, I'll start with the example. So, as I said before, in these diagrams, time flows upwards. Here we have a quantum input, because we're talking about quantum teleportation first. Here we have a shared qubit so Alice has a quantum input and a shared qubit with both. Alice does the measurement. Then we have an output with classical information represented by the area. And then Bob applies this mu, which is a controlled operation. So this is a 2-cell between a 4-dimensional classical structure and a 1-dimensional classical structure. So this is given by a vector of unitaries, because mu is unitary. And each UI is a morphism between B of C2 and B of C2 there. So this is exactly a controlled operation. So Bob applies this controlled operation, and then he has the output here. And this is the same by the equality as when the original system is transferred to Bob, and we have some uniform classical length. So when we don't have a quantum state but a classical state as the input, then this is classical encryption, where not much has changed, so we can just go. So what is left is to describe security of this protocol, which basically means that if we destroy the output, then all information is lost. This is expressed by this diagram here. So we get this implication by applying the trace map here on the output and here on the output. And on the left-hand side, we know that U is a family of invertible completely positive maps. So this is of course trace preserving. So we get this picture over here, and well, this follows immediately from here. So this gives us a unified security group. So just to summarize what we've learned today, we've given a categorical generalization of 2-hill based on modules. This was the construction 2, which preserves Dagger's compactness byproduct, and where the scalars of 2 of C correspond to the original modular category C. We can define horizontal composition in 2 of C as coequalizers, and these correspond to Dagger splittings. We've made some first steps in understanding 2 of CP star backfill, which is actually a very interesting problem. Also, we've shown that 2 of hill contains a subcategory of classical structures, matrices of special layer Frobenius algebras, and matrices of completely positive morphisms. And we've given a unified description of teleportation and classical encryption in this new model, and also a security proof of the teleportation and classical encryption. So, thank you very much.
Okay. Do we have questions? Yeah?
So what's the attacker model improving? So what is the attacker model you're proving security against? What does the attacker, what is he allowed to do?
Sorry.
What's the attacker model? What is the attacker allowed to do?
So if someone is somehow let's say that, disturbing the information flow, then it will get destroyed, and there will be that all information is lost. Yeah.
So it's a very strong attack model. You assume that the attack can do anything. The idea is, so it's a security property in this set. Suppose you've got this entangled pair. Suppose you lose or destroy the second member of this entangled pair. That's the same as just destroying the receiver. The point is that typical attackers only have access to the classical result of the measurement. If that's the case, then you may as well destroy the second part of the entangling state, and then it's equivalent to destroying the initial system. If the attacker has access to the second member of the entangling state, then yes, it's not secure against that attack.
But also in transferring the qubit from one to the other, the first content computation and then the attacker.
So there is no transfer of qubit. I mean, this is a pre-shared entangled state. So if the attacker can set that, then the game's off. So the powers of the attacker will see the attacker can learn how to do it.
So basically we improve if you destroy the qubit, you destroy the qubit.
Well, there's 3 qubits here. So the third qubit has to take from the first qubit. It also applies to classical encryption as well. Both the same things.
Well, perhaps this, if I understand the point, perhaps this could represent a kind of working principle for because typically the word security proof is loaded with much more modeling and quantitative thinking. So I think this was the spirit of the question, perhaps. Is there any other question? Well, yeah.
So when you first introduced the modules, you were saying that can you just explain again why we can see that as interaction with the environment?
Sorry?
This is at the very beginning when you first introduced the modules.
So why? Well, I'm not sure if that's the right question. So there are many interpretations of quantum mechanics, and we're just adopting one, which is the decoherency interpretation.
But when you first, a couple slides later, when you introduced these modules, you were saying something about them being an interaction with the environment just in these proofs and in these axioms?
Sorry?
Maybe I'll just ask you after.
Okay. Cool.
Yeah, it's actually in the same context. I don't think that the moment you introduce the modules, you already have interaction with the environment. The interaction with the environment only comes in the moment you do CP star, because that's when decoherence actually as an operation enters in the picture. That's the whole point of CPM, which is a part of CP star, is bringing in the idea that you have mixed operations, and decoherence is a mixed operation. And you don't have this here yet, but this is.
Well, these modules are the building blocks of our model. So these we definitely have to something, because they are the one cells. And I guess this is just a way of interpreting it. This is a way of making sense of it.
So my point is that you can't model noise with these yet. Noise only comes in when you go to the mixed state level, which happens when you do the CP star. So it's really then only that you model interaction with the environment, I would say. That was the whole point of CP star.
Yeah, in a way, you're right.
I mean, this is decoherence. It's a decoherence approach to computation of quantum mechanics. Whereas decoherence is entanglement of the environment in a pure state. That's the sense of the term. You can, of course, trace out the environment and then give it a state, which is also what's going on.
Is there any other question? Yes?
It sounds like you characterize the POVM in this diagram. Then how do you characterize the instrument?
An instrument? What do you mean with an instrument?
Instrument means comparative positive map varying the measure, normalized to be the trace preserver.
I'm not sure if I understand the question.
So the instrument will give the state after the measurement, because the QEM is only giving the probabilities.
As a given Juliet's talk, the POVM corresponds to destroyed measurement, but the instrument models the most general measurement.
So I'm not sure if I really understand, but so on the one hand we have the information about which output we get, which is captured in this area, because these are, well, the natural numbers that index the matrix, so they decide which Hilbert space is the output. And this line is the one cell, which basically captures all possible outputs.
Do you
So-
describe the state after the measurement?
This describes all possible states after the measurement at once.
Then it's not a POVM.
Sorry?
It's not a POVM.
So this is a destructive POVM. So the quantum system is gone and you've just got classical output. So quantum data comes in and classical data.
That means you don't have the state after the measurement.
Well, you do. But
If you describe state after the measurement and the probability for the outcome, it's not a POVM, but this is an instrument.
okay. You want to call this an instrument instead, I suppose.
Yeah. So basically, what I was trying to say is that this description corresponds to a sum of positive operators which sum to the identity, which is the definition of a POVM that I've been using. So I don't know how you want to call it.
Maybe you should not call POVM.
Okay.
So if I can paraphrase, I think the idea that this would be okay as a POVM, but the diagram before, that would be more like a quantum to classical channel. So neither an not a POVM, but just the channel from the quantum system to the classical setup. If I understood correctly, I'm not sure. Probably this was actually the point of Professor Zauer survey. So this is like putting all the outcomes together in a single stochastic process that is from quantum system to classical.
Right.
So probably we should be heading to lunch now. So let's thank again Linde and all the speakers.